The final properties of the waveguide modes I will show you is the modal effective index. The modal effective index NEFF is defined as beta over K. This is a very important parameter. Please keep in mind the definition. As we know, the transverse wave number in the coregion H can be expressed as this equation. And the transverse wave number in the Cladian region Q can be obtained by this equation. So, to make sure we have guided mode, I have told you H and Q should be real number. As a result, the beta should be smaller than N2K and larger than N1K to make sure H and Q, they both are real numbers. And according to this condition and by the definition of the modal effective index, you can learn that the NEFF will smaller than N2, the co-index, and larger than N1, the cladding index, for the guided mode on optical waveguides. This is the condition for the modal effective index. What is its corresponding physical meaning? Let's consider that in an homogeneous material, suppose the index of this material is N. If we have a plane wave propagates along the positive z direction, do you remember the mathematical form of this plane wave? It will be exponential minus j n k z, right? And now let's consider waveguide modes. If the waveguide axis is along z direction, so the waveguide modes will also propagate along the positive z direction. And we have learned that the z dependence of the waveguide modes can be written as exponential minus j beta z. And consider the definition of the NEFF. The exponential minus j beta z can be written as exponential minus j beta over k times kz, which is exponential minus j NEFF kz. Okay? And let's compare these two results. You will see that they have similar form. One is N, one is NEFF. So this means that as the waveguide modes propagate on the optical waveguide, it will just like the plane wave propagate in a homogeneous material with the index NEFF. Okay, let me say it again. As the waveguide mode propagates on the optical waveguide, it will just like a plane wave propagates in a homogeneous material of index NEFF. So the NEFF means that Even though the waveguide is formed by two materials N2 and N1. As the waveguide modes propagates along the waveguide, it will fill the average index of this structure, and the average index will depend on the field distribution of this waveguide mode. So this waveguide mode will fill an effective index of the total structure. As a result, the NEFF means that the effective index experienced by the waveguide mode as it propagates along the waveguide. That is why the NEFF is between N2 and N1. It should be the experience index by this waveguide mode on the optical waveguide, which is formed by material N2 and N1. Okay? Next, let's find out the model effective index of each waveguide mode from this figure. And please correct that this is M0, this is M1, this is M2, this is M3, and this is M4. Under this condition, we will have the normalized frequency V is 5.5. So we plot the quarter circle with the radius is 5.5. You will find out that we have 4 intersections with these small curves. And from the intersection, the position of each intersection, you can obtain their corresponding U value and the V value. And as I have said, from the U value and the V value, you can have the beta value. Okay? And you can see, as we increase the mode order from 0 to 3, we will have reduced the beta value. Because that for M0 mode, we have the largest value of V. Okay, compare these 4 modes. The M0 mode will have the largest value of V and the smallest value of U. As we know, the V is QD over 2 and the U is HD over 2, which means that M0 mode have the largest value of V and Q, and have the smallest value of U and H. By the definition of H and Q, largest Q means we have the largest beta. So as M increased, we will have smaller beta. As we decrease the mode order M, we will have the larger beta. Okay, so M0 mode will have the largest value of beta. By the definition of the NEFF, this also means that the M0 mode have the largest NEFF. So let me write down the NEFF of each mode. As you can see, as we increased the mode order, the NEFF will be reduced. So we know that as the M order is increased, we will have reduced the value of Q, and also the beta is decreased. By the reduced Q, we can also learn that as Q is reduced, what does the Q mean? The Q is the transverse wave number or in the cladding region. And if you remember, in the cladding region, the EM field will in proportion to exponential minus qx, right? So the decreased q means that the exponential function will decay slowly. Okay, so as we increase the mole number, the q number will be decreased and the field will decay more slowly into the cladding region. So from the mole field plotted here, you can see for 0 mole, for M0 mole, you have only one peak and the field decay rapidly in the cladding region. For the M1 mole, you have two peaks and the field decay a little bit slowly into the cladding region. And for the M2 mole, you have three peaks and the field decays very slowly in the cladding region. As for the M4 mole, M3 mole, we have four peaks and the field decay very slowly in the cladding region. Okay? So from the mole order, you can also predict the mole field in the optical waveguide. Besides, as I have said, the NEFF means that the effective index experienced by the waveguide mole as it propagates on this waveguide. The optical waveguide is formed by material N2 and N1. For M0 mole, you can see the field is well concentrated in the core region, so the M0 mole will experience more cladding material. The M0 mole will experience most of the core material, but experience a little bit cladding material. As a result, it will have higher effective index. For higher M value, take this one for example. The field will extend more into the cladding region, so it will feel more cladding material and less core material. As a result, the model effective index of this mole will have smaller value. Okay? So, by the field distribution, you can also predict the NEFF for each mole. This figure shows the model effective index NEFF at different value of the normalized frequency. And for M0, we have the T0 mole and the TM0 mole. For M1, we have T1 and the TM1. For M2, we have TE2 and the TM2. For different polarization, we can learn the following properties from this curve. First, as you can see, if we increase the value of the normalized frequency, which means that you reduce the wavelength or you increased the core size or you increase the core and the cladding index difference. All these ways will make the field guided more in the core region. As a result, we will have higher model effective index. This means that as we increase the normalized frequency, the field will guide more in the core region. So it will feel more index of the core material. As a result, we will have higher value of NEFF. Besides, as we reduce the mole order, if we reduce the mole order for the same effective index, for the same normalized frequency, for example, if the normalized frequency is 4, as we reduce the mole order, the NEFF will be increased. As I have said, for the same normalized frequency, if we reduce the mole order, the field will be more concentrated in the cold region. As a result, the NEFF value will be increased. Besides, for the same value of n, consider the same Moore order. We can find that the TE mod, the effective of TE mod, so I shall write it like this. The effective of TE mod will be larger than the effective index of the TM mod. From this curve, you can see for the same normalized frequency and the same Moore order, the TE mod is larger than TM mod. TE mod is larger than TM mod. This can be explained by the following figure. For TE mod and the TM mod, we have the optical waveguide shown here with the direction defined as this is Y and this is X. Due to the polarization, the TE mod will look like this, and the TM mod will look like this, according to the polarization. So as you can see, the EY field of the TE mod, it is well confined in the cold region, but however, for the ES field of the TM mod, it will extend to the cladding region. As the field extends more into the cladding region, so the NEFF will be reduced because it feels more smaller index material. Okay? So let's review what we have learned from this figure. You can see as we increase the normalized frequency, for each Moore order, the NEFF will be increased. For the same normalized frequency, if we reduce the Moore order, the NEFF will be increased. Besides, for the same Moore order, the NEFF of TE mod will be larger than NEFF of TM mod due to the Moore field distribution.